Okay, so you guys did reading on 1D arrays, right? Specifically row arrays and column arrays, and then some information that's kind of review. We already went over like indexing and deleting, adding elements, right? So one of the things that you read about was there are like other languages, multiple ways to do the same thing, right? So for doing some operation on an array, you can use a for loop like many other languages, right, that we're familiar with. And it would go one element of the array at a time, performing this operation, right? But in MATLAB, we can also do the same exact operation in a smaller code snippet and without a for loop by using array operations. Okay? And this is preferred in MATLAB because, as we know, everything in MATLAB is a matrix, right? And because of that, all of the operations are optimized to be done on matrices. So in the back end, from the compiler's perspective, this code on the right will run faster than this code on the left. So not only is it just easier to read, right? One short line. And just as long as you're in the mode of MATLAB, these are always array operations. I know that I'm going to do this operation of subtracting 32 and then multiplying 5/9 to all of the elements of the array. It's easier to read. So there's that, and it's faster. So this will not matter for an array of 4 elements, but as you get into more complex programming, then you have arrays of thousands, maybe tens of thousands of elements. It will matter a lot more. So when you're using MATLAB, try and avoid using for loops. Use array operations when possible. Okay. All right. So we already talked about array creation. And we also talked about how we can do this kind of indexing to create different arrays. But we did not talk about how we can make the iterator negative. Right? So this is going from 5 down to 0, and it's iterating by 1 for each element. So I go and make 5, 4, 3, 2, 1, 0. So this can be useful in some situations. And if you don't remember this, you can always just create 0 through 5, one step, and then there's a function flip left right. Right. And here's another example from 13 to -3, a step size of -2. So these are kind of perfect because I'm starting at 5, ending at 0, right? Step size of 1. My step size did not go outside of the bounds I specified, and neither does the 13 to -3. Okay. But if we say put 14 to -3 with the step size of -2, does it make the next element or no? Or does it give an error? 14 to -3. But what I mean is it's not perfect, right? So are you saying that it would not create an error and it would just stop at -2?
Yeah.
Any other opinion? This was in the reading, right? So what happens? Yes, so it does just stop at -2. So if you don't give it a perfect amount, it goes to where it can go, and it does not go beyond that. So if Adam, you're right, it would just go from 14 to -2. So it doesn't matter that we put -3 here. It would have been given the same result as -2, but if we put -4, then it would create 1 more. Okay? So just be careful when you're doing this. If you're giving it not exact step sizes, it will just go to where it can, as if you gave it those exact step sizes. Right? All right, so adding elements to arrays. This is something that we covered a little bit, but we did not cover exactly this. So we have a 3-dimensional row vector here, right? And we want to add one more dimension to it. We do that by just simply assigning that dimension a number. And it grows dynamically. We don't need to explicitly say that our array size is 4 from the beginning. And here's another example. So we want to add in the 7th index the number 80, but our original array is only 3 elements. What it does with the 3 elements in between, because it didn't have 4, 5, or 6, it just makes them 0. So it grows it all the way to 7, and 0 fills anything that was not already there. Right, so again, be careful. If you are assigning to a dimension far beyond the end of the array, you're going to get zeros in between. Deleting elements is kind of intuitive in MATLAB, but it's, again, not like other programming languages. For deleting an element, we just assign those dimensions to be an empty matrix. Right? So we create X vector 10 to 15. So it's going to create, and if you don't give it a step size, the default step size is 1, right? So 10 to 15, it's a length of 6. And then what we're doing here is we're saying from index 2 to 4, so 2, 3, 4, right? We're going to delete them. So this is 2, this is 3, this is 4. We're deleting 11, 12, 13. So that leaves us with 10, 14, 15. And now our length is down to 3. Right? So you can delete a whole range of indices by iterating over the vector in this way. Or you can also delete just individual indices by still assigning the empty matrix. Right? And the other things that you can do with this is if you want to get rid of all of the cases where A is exactly equal to 3. So rather than knowing the index of what you want to delete, you know the value that you want to delete, right? So this will give you a logical array where A is not equal to 3. And then by putting that logical array as indices into the array A, it will return an array, a subarray of A, where all of the elements that were not equal to 3 are kept. All the elements that were equal to 3 are not kept. So they're essentially deleted, right? And then here's another. So where A is equal to 3, make it empty. Right? So there's lots of ways to accomplish. Yes, Adam?
For the second one, does it like adjust all the elements? So let's say like, there's a 3 at index 4 and like a 3 at index 5. Does it like shift?
By the second one, do you mean this or do you mean this?
Yeah, at the A, in the parentheses, A equals 3.
This one?
Yeah.
So you mean here, so 1, 2, 3. Say this is A, right? And your question is, does it become 1, 2, 4? Or does it become 1, 2, 0? 4.
Yeah.
So what do we say? This one or this one? Yeah. Yeah, it deletes the element. And because we're assigning to that index the empty. Because what happens, what happens here, this gives us an illogical array of the same size as A, where it's zeros if A is not equal to 3, ones if A is equal to 3, right? And if you insert that logical array as indices into A, and then you're assigning something, that means that everywhere where that logical array is 0, the assignment will not happen. Everywhere where the logical array is 1, the assignments will happen, right? So for example, on the board, basically at index 3, the logical array is 1. So A at 3 becomes empty, and that is just deleting index 3, right? All right, so here are some more examples of multi-element indexing. So we have this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10-dimensional row vector. And here we're trying to assign 1 into 7 through 9. And it will write this, no problem, right? Because 7, 8, 9, that's a 3-dimensional array. 1, 1, 1 is a 3-dimensional array. So it will write ones to those indices in the array. But if we have 1 through 3, this is how many dimensions? And 5, 5 is. So we have a mismatching size. It's going to give us an error. Okay. Other things that you can use with these multiple element indexing is you can create these kind of index arrays. So the summer months are 7 through 9, right? The winter months, 12, 1, 2, right? So December, January, February. And now if you want to just get the electric bill from the summer months, you can just ask for the summer months. And that will return that subarray at those indices. Same thing with winter months. Right? One other thing that we covered very briefly was the end keyword. So here we have 1, 2, 3, 4, 5. And if we want the first sample, it's just getting the first element, right? If you want the last sample, you can use the end keyword. And then the last 3 samples is end minus 2 until the end. So if you're going to do something like this with the minus 2, the one thing that you have to keep in mind is if your array is only 2 samples, then this would generate index out of bound error. Okay. All right. These are 2 helpful functions. I just want to start with, do you remember this from the reading? Yep. Do we know what line space does? So I'll give you a hint. It takes in 3 variables. Let's open up that. To share screen. You guys extra tired today? All right, it's MATLAB on. Oh, I misspoke. Okay. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's what 10 is. And it goes from 1 to 5, right? So it just linearly spaces 10 data points between 1 and 5. So line space, what if I wanted 1 through 10, 10. What is this going to return? Just 1 through 10, right? So if this is what lin space or linear space returns, what do we think, where's my log space returns? Log space. What do we want to see? You want to see the same thing? 1, 10, 10. Okay. So this is 10 to the 10. So what did it return here? What is this?
Just like a really small number.
Yeah, but okay, let's just start at this end. This is 1, right? What is this? 10 to negative 1, right? 10 to the 3, 4, 5, 6, 7, 8, 9. Right? So again, there's 10 of them, right? So what are the first? No, not what I wanted. Let's look up exactly MATLAB log space function. Logarithmically spaced vector. Between 10 to the A and 10 to the B. And then there's n points. The log space 10 to the 1, 10 to 2. So this is 10 to the 1 is 10 to the 2 is, and then n, right? 10 to 100. And there's 1, 2, 3, 4, 5. And they're logarithmically spaced. Right? This one increases by 7. This one almost doubles, again almost doubles, and then almost doubles. Right? So we see the difference between lin space and log space. Alright, so other things that are helpful in MATLAB is we have element-wise operations. So rather than, again, writing a for loop to loop through two different matrices or two different vectors in order to do addition of two vectors together, if you have vectors A and B of the same size and you add them, the result will be all of the elements added together. Same thing for subtraction. And then if you want to do element-wise multiplication, exponentation, or division, you just have to put this dot before. So again, if we go to MATLAB, we create A is 1, 2, 3. A is 1, 2, 3. B is 4, 5, 6. If we do A plus B, right, we get a vector back. 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9. And also do A minus B, right? But if we just do A times B, they don't match dimensions for matrix multiplication, right? A is a 1 by 3, B is a 1 by 3. The 3 and the 1 don't match, so you can't matrix multiply. So it's telling you, maybe you meant to do this with the dots, which is element-wise multiplication, right? So 1 times 4 is 4, 2 times 5, 10, 3 times 6, 18. So if we did something like this, though, then we would be able to multiply them. Right? Because the multiplier operand with no dots is matrix multiplication. What I did here is I turned A into a 3 by 1, right? And B is still 1 by 3. And now 1 and 1 in the middle, they match. So you can matrix multiply those two matrices. And then the outside numbers tell you the size of the new matrix, right? So it's again going to be a 3 by 3. And that's what we get up here. So just be careful when doing that. If you want element-wise multiplication, you have to put the dot. Because it could be the case that you're trying to add a 3 by 3 to a 3 by 3, right? But if you don't put the dot, you will get the matrix multiplication of the 3 by 3 and the 3 by 3. So the same thing for if you want to do a power and if you want to divide. So here is some logical indexing. We went over this a little bit at the beginning, but here we have an array X, 3, 2, -1, 5, and 0. And here we want to do what here? What is happening to all of the elements of X?
Being raised to the power of 3.
Yes, raised to the power of 3. And then what's happening here? Yeah, 1 or 0, it's 1 when it's positive, yes. And then we element y is multiplying this with this, right? So this is going to get the third power of all of these elements. So 27, 8, -1, 125, 0. And then this is going to say 1, 1, 0, 1, 0. So when we multiply in the end, it gets 27, 8, and where it was not positive, 0, not positive, 0. Right? So y index, what are we trying to get here? Where y is 0, greater, so again, positive, and where y is less than 64. So here we're going to create a new array, Z1, that is from y, all of those indexes where all of this was true. Right? So here it's greater, it's positive, and it's less than 64. Positive, less than 64. Not positive, not less than 64. Not positive. Right? So we only get back 27 and 8. Right? Question.
Yeah, why does, D1 not just return first, like, why does Y, and then Y index not return just the first element?
Just the first element?
Yeah, because if Y index is, oh, actually, never mind.
Got it?
Yeah.
So here we're doing another example. So where x is positive and less than, and x is less than 4, right? So that will just be 3 and 2. So x index, so we get 3 and 2, but then here we're taking the third power. So 3 to the third power, 27, 2 to the third power, 8. So all of these were clear, right? But here we're kind of doing multiple steps in one line, right? So we're getting what's here. We want where x is positive and y is less than 64. And then we're grabbing all of those elements from y. So x is positive, 1, 2, 3. Y is less than 64, and 1, 2. So this results in just 1 and 2, and we're grabbing from y 1 and 2. So we get 27 and 8. So basically all it's saying here is kind of going to clean coding, which is what we're going to cover on Wednesday. On clean coding. Do something more like this. Like, these are the indexes that I'm interested in. I'm interested in indexes where y is greater than 0 and y is less than 64. And then in a different line, now I'm grabbing those values. And I can give a good name to this set of indices by doing this. But here I can't give them a name. Okay. All right. So that was the first two chapters of, or first chapter of 1D arrays, right? There are 4 more chapters of 1D arrays. You're going to read the next 2 for Wednesday, and then the last 2 before Friday. And on Friday, again, it's just time to work on a lab that you're going to work with 1D arrays. And I will post that lab soon, but it's just the Xylabs in the Zybugs. Because for the 1D array chapters, there's like 5 or 6 of them to do. Like last time, there was just one Xylab, right? But now there's 5 or 6, so I didn't add another thing on top of it. Okay. But just like we did for the last one, we're going to keep doing our own test. Okay. And we're going to, after Wednesday, I'm going to talk about clean coding. You're going to make sure that you're adhering to clean coding practices from that are there on forward as well. All right. So it seems we can end a little bit early. Does anyone have questions? Is there anything from the reading that you want to try on MATLAB in class?